Anybody actually get started on like the exam 2 over the weekend?
Nope.
Yeah,
I was like, yeah, I think since the 4th of July, I'll just have a couple days of summer.
Yeah, whatever. Don't be like
Carlos, I swear on my forefathers, I will start on exam 2 tonight when I'm back in Cincinnati. Swear on the souls of my forefathers, Carlos.
Okay, that's good. Yeah, you don't want to. I'm looking at the chat here. Yeah, that's good. You don't want to wait too long on that because that's as you can imagine, that's a pretty long one. Okay. So I'm gonna move on to our next topic now, which is heat transfer. Unless you guys have any questions for me, and then if we have time, there's still a lot more I'd like to show you guys in fluid mechanics. But I need to make sure I teach you guys some stuff in heat and mass transfer. Just in heat transfer, nothing on mass. Mass transfer is transfer too. Okay, so let's get started with some of the more obvious stuff. Heat conduction, it's pretty straightforward with a few things. By the way, this textbook here is one of the best textbooks in heat transfer. Most of the students who use this textbook are actually mechanical engineers. But remarkably, when I was an undergraduate, way back in like 1992 or something like that, I actually used, I think, the first edition of this textbook a long time ago. I still have the first edition of this textbook, I think, somewhere in my office, maybe. But from elementary school, you guys know there are three main modes of heat transfer. The first one is basically by conduction, where you either have a solid or a fluid. Even water and air actually does have conduction, in which heat passes through, right? And then the other form of heat transfer, right, is in the case of convection, in which what happens is you got a surface here, and you got like a fluid, water, air, liquid or gas flowing over that solid, and you have heat transfer. Now you might ask, hey, when you have convection, does conduction occur at the same time? Yeah, absolutely. So let's say if there's liquid flowing across through that, does conduction take place through the liquid too? Yeah, of course. But what happens is most of the time when people talk about convection, the conduction is occurring too, but it is the movement of the fluid has a tremendous impact on the rate of heat transfer. Okay, so that's convective heat transfer. And then one of the most important modes of heat transfer, which unfortunately we don't have much time to cover in this class, is called radiation. But it's by heat transfer by radiation. And heat transfer by radiation is predominant at very high temperatures, right? So for example, if you're grilling, for example, or if you're using an oven and you're using a broiler, especially the broiler, like where you're using the coils on top of the oven and heating those up. And the main mode of radiative transfer between those coils and let's say your steak, that thing is by radiation, for example. All the heat that comes to us from the sun is by radiation. So the radiation can take place through a vacuum, basically. It also passes through an air. It can actually passes also through some liquids, but most liquids block out the radiation. Okay. So that's the quick, kindergarten introduction to heat transfer. Okay. In this textbook, they talk some more about some of the details of conduction, right? So here's the first place we start talking about some form of an equation in conduction. Okay. And this one here is called the Fourier's law. This thing is very, very important, right? It's called the Fourier's law. Okay. And you'll notice that in this textbook, let me move this a bit smaller here. Okay, I hope that's not too small. Okay. So in this textbook here, you'll notice they have the following nomenclature, right? Their nomenclature is Q. And then the next thing that they have, right, is they go off and put two apostrophes above that. And what they are denoting by that is basically flux, right? It is a heat flux. And then you'll notice here, this thing is the direction of it, the direction. The heat flux in the x direction, right, is equal to the minus the thermal conductivity, so that guy there's the thermal conductivity, right, multiplied by the gradient in the temperature, dt dx, the gradient in the temperature. And an important thing to notice here is that there's this negative sign. There's this negative sign there. That negative sign is very important. Okay. So the first thing to notice here is that they have a typo here. They're missing an X. I'm just kidding. So when they say heat flux, what are the units of heat flux? Okay. Now the key word to remember, right? The key word to remember in transport and engineering, right, is the word flux, right? When someone says flux in engineering, right? Let's say magnetic. A flux is always refers to something on a per area basis, right? So when someone says heat flux, they're referring to that as basically joules. It's a flux, so it's per area, so per area per second, okay? So when someone tells you the flux, it's per area per second, heat flux. So in contrast with heat flow, when someone tells you heat flow, that's basically the total joules per second or watts. When someone says flux, it is on a per area basis, okay? That is on a per area basis, okay? So that thing is the same as watts per square meter. And that's basically the units of the cat just passed through, okay?
So a flux capacitor operates on a per area basis, right?
Depends. If it's hooked up to a DeLorean, yeah, it is.
Yes.
I don't know if you guys saw the cat, so let me show you guys the cat.
Yeah.
See everybody in class? There you go. All right. Okay. Piper, huh? What do you think? You okay? You want the teacher's class? Yeah? All right. Come. Oh, there you go.
That's going to be one enlightened cat, Carlos.
I know, especially if you attend every class, right, Piper? It's like right next to me right now. Okay. Yeah, all right. Okay, let's keep going here. And so the next important thing to notice are the units, right? The units are crucial here. Now, you'll notice that this thing here is the gradient, right? So you're like wondering, what on earth does that mean? Well, it's pretty fair to, let's do some common sense thing, right? So let's say you have a bar, right? So let's say, you have a bar, right? And on one side, so let's say this is the x direction. And let's say this is x is 0 here. Let's say x is equal to 10 meters, let's say. And on this side, let's say you have 200 Celsius. And on this side, let's stick with kelvins. So let's say here you have, let's say 600 kelvins. And on this side, let's say you have 300 kelvins. And so when you go off and make a plot of that, how does that look like? So you'll say, hey, when x is 10 and x is 0, this thing is at 600 kelvins. And down here, this thing is at 300 kelvins. So I have my 2 points, let's say. For now, let's say it's a straight line, right? So it's a straight line. No, it's actually a hyper, because he loves keyboards, okay? Yeah, and so what happens is, so on this side, the temperature is 600. On this side, it's 300. And you're going from 0 to 10 meters, right, in position. So now you notice, when someone tells you, I know, like right now you're asking me, Carlos, how do you know it's a straight line? Well, we'll talk about that in a bit, okay? We'll talk about that in a bit. But what happens is that, let's say if it is a straight line for now, right? What do you expect? Well, you expect heat to conduct from high temperature to low temperature, right? And so you expect, in this case, the heat flow to be in this direction, right? So which direction is that? Notice that thing is in the direction of negative x, because we're going from 0 to 10. This is the direction of positive x, right? Our heat flux is in the negative direction. Did you see? Heat flow from hot to cold. So it's going to be negative of the gradient. And so this derivative here, you got the negative because the heat flux is going from higher temperature to lower temperature. This negative sign here is absolutely crucial. Okay. Now you might ask, well, what if things are more complicated? Let's say I have some complicated shape. If you have a complicated shape, let's say the cross-sectional area is not uniform or things like that. Or let's say the material has a thermal conductivity that varies with position or things like that. Then what's going to happen is that you could have a temperature profile that's not necessarily linear. Then in that case here, your heat flux here, it's going to be dependent on the slope, and your heat flux here is going to be dependent on the slope, right? And so your heat flux is the local derivative. So it is the local slope or the derivative of the temperature with respect to position. Okay. And this guy here, that's just basically Fourier slope. Okay. And if you guys have ever heard of something called the Fourier series, which is basically how you can have a function and you can approximate that function using a sum of sines and cosines, or sinusoidal function. That's basically the same Fourier series. It's the same Fourier. And what happens is actually amazingly, well, not so amazingly, what happens is that like all of these things you guys might have heard about Fourier series, how you can decompose like a time series into a sequence of sines and cosines, was actually developed by Fourier, the same guy, actually to solve the heat diffusion equation. So the main purpose of the Fourier transform or the Fourier series was actually to solve the partial differential equations in heat transfer. And this actually later on, that's actually more used in signal processing, for example, or in music, for example. All right. Good enough. So that thing is the heat flux, Fourier's law, very important. Okay. Now, and also the other thing is the units, right? So let's work out the units fully here, right? So let me write it down again. So you have heat flux minus K dt dx, right? So I think when I'm teaching, my cat just falls asleep. He's all knocked out and sleeping right next to me now. It's hilarious. He's just all sleeping, you know. You guys see it? He's awesome. Well. So let's talk a bit about units, right? Oh, I was showing you the cat sleeping. Oh, sorry about that. We'll do that some other time. Let's focus on class for here. And so you got the heat flux. The heat flux is watts per square meter, right? Again, every time someone tells you flux, it's always on a per area basis, right? And then what are the units of the derivative? Well, temperature is in kelvins. Distance, of course, is in meters, right? And so what are the units of K? And so you'll notice here that the units of K, the units of the thermal conductivity, must have units of watt, meter, Kelvin. Okay, so that's the units of thermal conductivity. Okay, and that's over here. So the units of thermal conductivity are watt, meter, Kelvin. Okay. Okay, it's a characteristic of just the material. Okay. We'll be going through more details here. So let's scroll down a bit. Okay. Yeah, so here's just a very practical example. They just tell you, hey, you got a wall. On one side is at 1400 kelvins, and the other side's at 1150. You're given the thermal conductivity, and in this case here, we're just going to say assume here for now that the temperature profile is indeed linear, right? And we will talk about why it is a linear temperature profile later on, right? Hey, don't eat my Apple Pencil. Okay. Yeah. And so from here, you can calculate the heat flux based on the thermal conductivity and the gradient in the temperature, right? So it is the change in temperature over the distance. That's a derivative, and that's how you calculate the heat flux. Okay. So now, let me ask you guys a common sense question. Okay, let's talk a bit about common sense questions. Okay, so let's say on this side you got 1,000 kelvins. It's hot, right? And then you got 1,000 kelvins, and you got a wall, right? And on this side here, if let's say this is so the in both cases the thickness of the material is the same, L. You have the same thickness. And then someone tells you, hey, on this side you have this is low. You have a low thermal conductivity, and on this side here you have a high thermal conductivity. Which one would you touch? Yeah, of course, you're going to touch the low thermal conductivity, right? Because of what happens is basically when thermal conductivity is low, that's basically a heat insulation, right? So that you might put in something like styrofoam or something like that. That's what a styrofoam would melt at 1,000 kelvins. So you need something, you need to like a porous ceramic, for example, right? So if you have an insulation, what that thing does is it causes so on this side you might have let's say a temperature of let's say just like a temperature of let's say 100 Kelvin, no, maybe a 300 Kelvin on this side. But in contrast, on this side here, if you have a high thermal conductivity, this might end up being 900 kelvins, for example, a high temperature, right? Okay, and we'll talk a bit some more about that in a moment. Okay, all right. So let's keep going. So that's a quick introduction to conduction. We're going to go through a lot more details, right? So right now we're just going through this. The next topic here is this idea of convection. Now, in convection, convection is actually extremely complicated in the sense that, like, when you have a surface here, for example, so if you have a surface here, well, what's going on? Like right above the surface, right, is right at the surface, the velocity of the fluid through it has zero velocity, right? And as you go further and further away from the surface, eventually you go sufficiently far enough, the fluid does not even know that there's a surface there, right? And the distance from the surface beyond which the fluid doesn't sense the presence of the solid plate of the surface, that's referred to as a boundary layer, right? So you notice this is the velocity distribution. And once you reach a certain distance from the surface, the velocity is no longer perturbed. And so over here, you see this label here, U infinity. That's referring to basically as the velocity in the x direction, infinitely far or sufficiently far from the surface so that the velocity is no longer influenced by the surface. And this thing is referred to as a boundary layer, right? Now, on this other side here, let's say if this temperature here is, let's say, it's a hot surface, for example, and your fluid is flowing through it, it's colder. Well, the temperature right at the surface is the temperature of the surface. And then as you go further and further away from it within the fluid, the temperature goes down until you reach this label as T infinity is basically the free stream temperature of the fluid. The fluid's temperature as if it never noticed the presence of the surface, right? And so there's this particular boundary layer thickness, right? Between what you can say as the surface temperature and a free stream temperature sufficiently far enough away. Now, you can imagine that the exact calculation of the heat transfer here is very complicated because that would involve simultaneous differential equations, partial differential equations to be solved for both the velocity profile and also the conduction that takes place. So actually, when you have something called convection, like right at the surface here, you have a combination of conduction taking place within the fluid, which is basically moving. Right. So when you think about convection, what's actually going on is that you're basically combining the effects of conduction over very, very, very small control volumes. And the numerical solution of that or computational solution of that basically leads to an over effect that you characterize as convection that is over and above what you would just observe heat transfer by conduction through the box stagnant fluid. Because the movement of the fluid carries with it the thermal energy over and beyond what is just heat transfer by conduction through the fluid. So that's what's going on there. Now, the details of this is quite complicated, and there's no way we could easily cover that in this class. And especially now that you guys don't take multivariable calculus, it's really, and you don't take partial differential equations, it would make, totally no sense when you see the equations to be solved to get at the temperature distribution and velocity distribution, even say simple as something like over the flat plate. But the solution of this heat transfer by convection over flat plate in laminar flow is actually, I used to teach that actually several years ago at the undergraduate level. It's called the Blausch's solution. I would usually teach that in transport too. I've not been doing that for probably the last 5 years, 6 years now, just because you guys don't take multivariable calculus anymore, and it's too hard to teach it when you don't have the mathematical background for it. So let me scroll down a bit some more. Now, what happens is that in this class, especially at the undergraduate level, what is done is that the complexity of this heat transfer by convection, right? We completely hide that away. And we hide that all away and put that into this, this letter H, which is referred to as a heat transfer coefficient. So when you have the case of convection, right? And you want to stick with just a TV7 version of it. So this is the TV7 version of convection, right? So you guys know what a TV7 rating is, right? That's basically Tom and Jerry on Disney Plus, right? That's my favorite movie, right? That's my favorite channel, Tom and Jerry or Roadrunner. Okay, and so if we stick with just the TV7 version of this thing, what's going to happen is that your heat flux, right? So this thing is still watts per square meter, right? It's just some heat transfer coefficient, H. So this thing is referred to as a heat transfer coefficient. Heat transfer coefficient, right? Multiplied by just a very simple thing, just like the temperature at the surface minus the temperature at far enough away from the surface. So of course, your immediate question would be, Carlos, how far away exactly from the surface do I have to go before I can get to infinity? What is this so-called boundary layer thickness in which I have to go far enough away? What exactly is the calculation of that boundary layer thickness? And actually, how do I calculate from first principles this H? Well, that is seriously X-rated material, right? I think to really much of that thing could actually be graduate school material, right? To really understand the mathematics of that thing. But it's doable, especially in laminar flow. For turbulent flow, it's extremely complicated. Okay. But what I can do here, what we can do is we can give you like typical values. But before we get too carried away with this, let's take a look at the units, right? So the units of that is in kelvins. And so the units of the heat transfer coefficient is actually watts meter squared Kelvin. And you should contrast that with the units for thermal conductivity. The units for thermal conductivity, as we showed earlier, was watt meter Kelvin. There's a difference, okay? Now, let's take a look at typical values for a heat transfer coefficient. So if you just have a free convection, right? Free convection, what is free convection? Well, there's this whole thing about hot air going up because its density is lower, right? And even for liquids, you will have some recirculation because of different densities of liquids, hot and cold liquid. And so if you're dealing with just free convection where you're not purposely stirring it, these are like the typical values for the heat transfer coefficient. And when you have forced convection, you turn on your fan, you're pumping water over it. The range of the heat transfer coefficient is considerably more different, considerably higher than in the case for just liquids. Now, if you have like computers, nowadays it's not just gaming computers. Like a lot of CPUs nowadays on desktops that you purchase are actually quote unquote liquid cooled, right? Who among you guys have a liquid cooled CPU on your desktop like I do? Anyone else? God, seriously, none of you could play video. None of you play enough video games to warrant like a water-cooled CPU. My gosh, no wonder you guys don't do well enough in school because you don't play enough video games. I'm not kidding. Okay.
Yeah. I'm played a single game all semester. I know I need to fix that.
Well, you got to understand, liquid cooling is heck of a lot. It's pretty cheap now. I mean, a liquid cooling on a CPU is you could put one on for about like, I don't know, cheapest was probably $50. That's all it costs. But, and this is one of the biggest misconceptions, right? So a lot of people just don't quite understand when people say liquid cooled CPU or desktop, what exactly does that mean? My cat loves the sound of my voice. He's just dead asleep next to me. All right. So what that is it goes like the following, because you look at this, you say, hey, forced convection is a lot higher for liquids than, for example, for gases, right? So for example, it goes like this. So let's say here's your computer chip there, right? Okay. So I always used to use an Intel chip, but nowadays I no longer use Intel inside. So let's say this is an AMD 6600 processor, for example. All right. I always used to use Intel i7 or i9s in there. Okay, no more. Okay. I'm AMD fan now. Okay. So there's your chip. Now, the okay. Okay, don't click on that link. I have no idea where that goes, Nick. Okay. Okay, so here we go. So what happens is you got to remember, right? So if you put your fan over there, so there's your desktop fan, and you blow air over that, right? You see the problem you have. The problem you have is that, let's say this chip here is the temperature is, let's say, 25 Celsius. You got okay air conditioning. Okay. Now what happens is that your chip generates heat, right? Your chip is going to generate heat because you're playing some video game, right? Okay. And so your chip is generating some heat. So how much heat is getting generated? So let's say you are generating, I don't know, let's say you got 200 watts. Yeah, fine. Let's say you got some, big thing going on your CPU. So let's say you got 200 watts. Okay? And so you need to dissipate that, right? So you need to dissipate that heat. And so what do you do? And so what's going to happen is that you got your heat flux. You got your heat flux. Remember, heat flux is watts per area, right? And then you multiply that by the area, right? And then you remember, hey, the heat flux is actually the heat transfer coefficient times the temperature difference. And so now when you talk about the temperature difference, which one is that? Well, this is T infinity. That's the air that's flowing. And then, so what's the temperature? This is going to be your surface temperature, Ts. So you got Ts minus T infinity, right? You see how this thing's kind of going to work? Now, what happens is that you're blowing air over your CPU. So you're blowing over air over that. So, okay, fine. So let's say you put in there 200, right? So you got 200 watts, right? And here you got a 200 watts per square meter per Kelvin, right? Then now you got the area. Oh shucks, you got an area problem. Okay. And so how big is a CPU? Let's say that's about, I don't know, let's call it, let's say 2 centimeters. Okay. So your area is going to be one side's 2 centimeters. So that's going to be four square centimeters, right? So your area is 4 cm squared. Okay. That's your area. And then now you got the surface temperature of your chip minus 25 Celsius, let's say. Okay, now what's 4 cm squared? 4 cm squared is 4 10 to the minus 4 square meter. So what do you have? So you have 200 watts is equal to, what's that going to be? So there's 2 zeros there, so you're going to have 8, 10 to the minus 2, Ts minus 25. You see where we're going here? You see what kind of a big problem we got here? Anybody see the problem we got? We got a serious problem here. It's gonna melt. Why? I can yell as much as I want. The cat's like dead asleep. But the moment I walk away, he wakes up chasing me. Anyways, so tell me, why do we got a problem here? Oh, we got a serious problem here. You move that to the other side, you got 16, you got freaking 10 to the fourth is equal to TS minus 25. Holy moly, your chip's gonna melt. I mean, forget about your chip gonna melt. That's hotter than your grill, than your charcoal grill, man. Seriously, that's seriously hot. There's no way you're gonna get there. Okay? All right. So, the surface of your computer chip is just gonna melt this thing. Totally melt this thing. And so what do people do? So your next option is to basically put down fins. Have you guys ever seen fins for computer chips? Or amplifiers? So basically what you do is it's usually aluminum, right? So you go off and get a block of aluminum that's like this. Like this. It kind of looks like a torture device, a modern torture device. It's something like this. It's not very sharp. You know what I'm talking about, right? And it goes like this. I can't draw that, but it's basically fins. And what this thing does, heat sinks. Exactly, you can call that a heat sink. Yeah, you can call that a heat sink. So what all this thing does is that so you basically have these have these things, and what you do is you use a glue, you use a thermal paste, basically glue that has a lot of metal particles in there, or graphite or carbon, and you glue that or put that on top of your computer chip. So you put that right on top of your computer chip. Well, what does that do? Well, earlier our area was 2 cm by 2 cm. Our area earlier was 4 square centimeters. By putting all those fins in there, you basically increase the effective area, kind of. Of course, it is not perfect because you expect some temperature drop because of the conduction through the metal. Usually that's made of aluminum, so it's good conduction, but still there's some temperature drop. And so the purpose of fins is to enhance the effective area. Okay, so that's one way to do it. But still, in most situations, that's not really adequate, especially if you're putting in a lot of power on your chip. And so the alternative that is done is the following. You basically, the alternative here is so if this is your CPU, right? The alternative thing is to basically get what you have here is kind of like a box, something like this. And that's typically made of metal. So the bottom surface is made of metal, so there's good contact, thin good metal, and you got liquid that flows in and liquid that flows out, right? The metal to metal contact between the liquid cooler and the chip is very thin and very good metal conduction. And so there's minimal temperature difference between the surface of the chip and this lower surface of that liquid cooler, should you call it that way. And so when liquid passes through it and liquid passes out, the effective heat transfer between the chip and the liquid is basically becomes something that is done by convection. And that can be considerably higher depending on the flow rate of the liquid. Then now you might ask, well, wait a minute. I mean, I'm not going to have a bucket of cold water like continuously passing through my chip. No. And so what happens is eventually this water here, or that coolant liquid, is basically passed through something. Have you ever seen the radiator of a car, or basically the air conditioner on the outside of your home, right? Or air conditioning on your wall air conditioner? You basically you go off and pass this liquid through like a lot of a very, very thin pipes, right? And you pass it through. And what happens is that you blow air over it. So you blow air. So that's your radiator. So all a radiator is a heat exchanger, providing a lot of surface area, right, for the liquid that's passing through and the air that's blowing past for there to be heat transfer, right? So what happens is basically, so when you have a liquid-cooled CPU, what you're basically doing is, in this vicinity here, right at the chip, you don't have much surface area. within your motherboard, you don't have much surface area to enable the cooling. And so what happened is that with that limited surface area, you switch to liquid cooling so that your heat transfer coefficient is higher. But once you carry that liquid out, let's say to the back of your case, so usually at the back of your case, you'll have a radiator there, just like exactly the same as a car radiator, where you have the coolant passes through with a lot of surface area. Then here you can blow air through that, and you're no longer constrained by the tight volume right above a chip. This radiator here, that could be as big as you want it to be. There's no limitations at that point, right? Some people fill their water cooled mineral oil. So what happens is that the choice of coolant that you want to pass through there, there's many choices for that. Well, one of the main things is that basically you have a pump through that liquid cooling system. And so what happens is that you have these hoses, right? And what happened is that, remember, you run your PC for like years, right? And so these hoses here typically have to be some sort of flexible plastic because you got to wire that up inside your PC. And so the flexibility of these tubing causes some of the liquid, whatever is in there, to evaporate out. And what happens is eventually your lines are no longer completely filled with just the liquid. Then, of course, the efficiency of the cooling degrades. But way before that happens is that you're going to have air bubbles in there. And when the air bubbles passes through the pump, you're going to get something called cavitation. And that is extremely, extremely noisy. It's so annoying, right? And so some people might change the liquid coolant in there into something with less volatility or something that is less permeable through the hoses. So some people use mineral oil or things like that. With me, I just usually swap out my water cooler. Time passes by. It's a pain to replace those, but they're not expensive. Okay. Let me see. But yeah, you could use bleeder valves. There you go, Tim. With this, Tim. There you go. I'm sure you have one. Yeah, you could do stuff like that too. There's a variety of things you can do there. Okay. Now, of course, everybody noticed is that you got the 100,000-pound elephant in the room, which is basically this guy here. So you look at that and say, hey, if I ever want to do heat transfer, right? The big king of heat transfer is heat transfer with phase change, either by boiling or condensation. Okay. And so one of the first things you'll notice is, what do you mean by boiling? Well, see, if you got a pot here, so you got your flames going in your water pot. What happens is the bottom surface gets hot, you go off and start forming water vapor, and that water vapor goes up. So basically steam, water vapor going up the liquid. And that causes quite a lot of turbulence and basically motion, mixing effects right at the surface. And that's basically enhances the heat transfer at the surface there. You got bubbles, water vapor that's forming and going up. And so that renews the surface there. There's a variety of boiling regimes, right? So I'm not film, pool boiling. So I'm not going to go through that here, but it's about I don't know, 2,500, they say. But the big kahuna here is basically condensation. Okay. By the way, who likes dim sum? Who likes? Well, so Hannah and Vu, I mean, both of you have had the opportunity, I think, to go to UBC in Vancouver. The best dim sum in the world is in Vancouver. That's the main reason I go to Vancouver. Then I visit my parents and my brother. But I go there to eat dim sum. Okay. And so, I'm already getting hungry hearing this. Okay. But anyways, so the idea, so this, in this dim sum foods, Chinese foods, they got the food, and it's usually all pre-frozen, pre-made frozen foods, and then they go off and put it in a big steamer. Okay. So this actually used to be an exam question a long time ago. And it goes like this. Let me see. Who was looking at me? Okay. So let's say, Emma, you were giving me you're frowning at me for a moment there. Let's see. So Emma, you got hired by the Cincinnati Egg Company. Okay. And so what happened is you have 10,000 eggs and you got to hard boil it. So you want to hard boil 10,000 eggs. What are you going to do?
Get a really big pot.
Yeah, you need a big pot, but then are you gonna put boiling water in that thing?
Yeah.
Oh no, you don't do that. So of course, if you check online, like if you look at your egg cooker or online, everything's by steam, right? So let me check here. So let's go egg cooker, right? Egg cooker. I don't know, egg cooker. Do they sell such a thing? Oh yes, check this out. You see, they got a Hamilton egg cooker. Did you see? So this one can cook. I don't know, like that looks like I don't know, like 10 eggs, maybe 12. Yeah, so that's a rapid egg cooker. So notice they say rapid egg cooker. So what do you think happens there? They steam the eggs, right? You got to steam the eggs. And so what's the advantage of steaming? Well, see, the advantage of steaming goes like this. So if here's your pot, right? You only need a small amount of water, right? You don't want too much water. Because the more water you put in, you got to bring up all that water to 100 Celsius, right? To the cooking temperature. So that takes a long time because the heat capacity of water is fairly high. And so what happens is that if you only put a small amount of water in there, you only need to bring up a small amount of water to 100 Celsius, at which point it starts boiling. And then what happens is that you got your egg. I don't know how to draw eggs. Okay, but anyways. So anyways, you stack up your eggs, right? You stack up your eggs, and what happens is that the steam, right? The water is boiling, so you got the steam coming up, and the steam condenses. The steam condenses on the cold surface. That thing has the highest heat transfer coefficient. That's about 100,000. So if you ever get somewhere and you need to get tortured and you have a choice of sticking your hand into boiling water or putting your hand above vigorously boiling water, well, you always stick your hand into the boiling water. That's a lot better. You stick your hand into boiling water, you're at about 2,500. You stick your hand above steam that's condensing on you, oh my gosh, that's 100,000, right? So steam burns, getting burned by steam is a lot more dangerous than getting burned by hot water. So if someone throws 100 Celsius hot water at you, you get doused with 100 Celsius hot water versus you got doused by like a hose that's shooting out steam. Oh, take the hot water anytime. The hot steam coming at you is a lot worse. Much worse.
How?
Did you say how or ow?
How exactly?
I'm not sure I understand that, but I'm just stating the facts here. I'm not explaining why.
Oh, but yeah, seriously though, ow.
I don't know. Try it.
I said I said ow that time.
All right, fine. Let's keep that as ouch. Okay, so we don't make it confuse here. Okay, ouch. Okay, so let's keep going here, right? So that's just so if you're cooking stuff, yeah, steam. Steam is fast. Okay, steaming is the fastest way to cook, in my opinion. Okay. All right, so let's move down. By the way, do you guys do the microwave steamer? So when you cook stuff in the microwave, you know what I always do? Always paper towel, wetted paper towel over everything. Wetted paper towel over everything. Keeps the mess away, speeds up the cooking. Yeah. So microwave.
And you don't get wait, do you get paper towel bits in your food ever?
Just eat it. It's okay. Yeah, it's okay. Paper's nutritious, fiber. The next thing is extra protein. No, it's fiber, cellulose. I just don't want the colorants. Okay. So now the next thing is basically heat transfer by radiation. Okay. And I always jokingly remember this thing as the 5.678 thing. Okay. And so so if you have a surface, right? So if you have some surface, right? If you have some surface and this thing is at some temperature, right? This is going to emit radiation, right? And so what happens is that if you have something so-called a perfect black body, of which really only carbon black is, right? But let's say if you have a perfect black body, So if you have a perfect black body, right, it's going to emit radiation, right, following Planck's black body radiation thing. So it's a Planck black body radiation. Okay, images. There you go. Lots of beautiful images here. Let's say this guy here. Okay. I want this bigger. Okay. 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 And so what happens is that if you have a black body, now you might be wondering what on earth is a black body. So the perfect black body is basically carbon black, right? Carbon black approaches a black body. Like asphalt gets close to that, right? And so what happens is that if you got a black body, it's going to radiate at different wavelengths of radiation. And depending on the temperature, it's going to emit the intensity of radiation at every wavelength. It's going to look like a curve like this, right, at different temperatures. Now, what happens is that in this class, we're not going to go into the details of like the energy at the different wavelengths, but rather we're just interested in as basically, hey, radiation is radiation. I don't care what wavelength it is. Just give me the total power from that radiation. And so what's done here is you go off and integrate Planck's Planck's equation. Where's that equation go? So you go off and do the integration on this expression here. Where's that expression? There you go. So you got this equation here, right? So you integrate that thing with respect to lambda, right? With respect to the wavelength. So when you go off and integrate this expression for the energy as a function of wavelength and temperature, so you pick a temperature fix and you integrate this expression with respect to lambda, the wavelength, from basically 0 to infinity over all wavelengths, right? Well, you all have to go to the limit of 0, not exactly at 0. Of course, you have to do this in the limit, right? And so if you go do that, amazingly, the expression is ridiculously simple. The integration looks something like that. The integration is basically the temperature raised to the fourth power multiplied by this constant, this sigma constant here, which is referred to as a Stefan Boltzmann constant, which is 5.67 times 10 to the minus 8 watts per square meter. So that's a flux per Kelvin to the fourth. Okay. Now you'll notice that the emissivity, right, basically the watts per square meter, that the energy that's being radiated out per square meter, the power per area, that's the flux, goes with the temperature, to the fourth power. So if you have, by the way, every time you have a temperature being raised to some power or you're multiplying by temperature, of course, that always has to be in kelvins, right? You cannot go around multiplying, square rooting, or raising temperature to some power unless it is in kelvins. So this temperature has to be in kelvins. Now, because you're raising that thing to the fourth power, so if you increase your temperature by a factor of 10, well, you just increase the emissivity by 10 to the fourth, 10,000. So if you increase your temperature by a factor of 10, you increase the emitted radiative power by 10,000 times. So hot objects tends to emit a lot of radiation. Heat transfer by radiation is very significant once you go up to high temperatures. But at lower temperatures, it's negligible, right? But even then, you can still feel radiation, right? Okay. So let me go on a bit some more here. I got 10 minutes here in today's Mickey Mouse class, right? Today's like a relaxing no equation day, right? And so what happens is that, as I said earlier, this thing is for a perfect black body. And so what happens is that in most situations, right, you need a correction factor for that because most surfaces are not perfect black bodies. And so you have this thing called emissivity, right? Emissivity, right? So you have something called emissivity. Different surfaces have a different emissivity, right? And it goes like this. Emissivity is just a correction factor. Now, in reality, right? When you have this approximation here where you use some value for the emissivity. So let's look at typical values for emissivity. So emissivity. Let's say aluminum. Yeah, let's take a look at aluminum. Excuse me. So if you have like a highly polished aluminum, like aluminum foil, your emissivity is pretty low, let's say 0.04, 0.05. But if let's say you have anodized aluminum, do you know what anodized aluminum is? Well, anodized aluminum is really just has aluminum oxide on the surface, right? So it's black. Most anodized aluminum is black because it's no longer aluminum, it's aluminum oxide on the surface, it's black. The emissivity goes up to about 0.77, right? And there's a lot more, materials here of different emissivity, right? So I think carbon black, carbon goes up to about 0.98, right? 0.98, I think that's about as high as it goes. Or is there higher ones? I think carbon black, right? So these are the typical emissivity coefficient. Now, what most people don't say is that the emissivity actually depends on wavelength and also depends on temperature, right? So in these kinds of tables here, you're not seeing the true complexity of this because you're only being given one value independent of wavelength and temperature. But the reality is it depends on wavelength and depends on temperature. Okay? Now, so there's this story of emissivity there. Now, let me ask you this. When you guys are in organic chemistry, do you guys do distillations? Or reflux or distillations? You guys do distillations, right? Do you guys use aluminum foil? Of course, you use aluminum foil. Of course, what do? You always wrap. So here's your RV flask, right? And here's your condenser. You always wrap that thing up with aluminum foil, like as much aluminum foil literally as you could, right? And you might be wondering, why on earth am I gonna wrap that thing with aluminum foil? Because, okay, kitty. Oh, okay, he's gonna walk over my kitty. Okay, so he just goes that way. He's getting hungry. Charlie, can you go feed him a bit? Okay. And so what happens is that aluminum foil, well, what happens? Well, if you don't have the aluminum foil there, you have glass. Well, glass, this gets hot. So the glass is gonna radiate heat, right? So if you look at the emissivity of glass, where's the emissivity of glass? Glass. So Pyrex glass, emissivity is about 0.9. Did you see that? So if you look at Pyrex glass, that's about 0.9. So you can, so even though Pyrex glass looks transparent, it doesn't look black at all. Oh my God, it gets pretty close to a black body. So that thing is, if it's like 400 kelvins, that's 400 to the fourth times the 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. You multiply that together, that's the emissivity times 0.94. But if you go off and wrap that thing up in aluminum foil, well, the surface is not aluminum. What's the emissivity of that? Well, that drops all the way down to about 0.0 aluminum, I don't know, 0.05 or so. And so you significantly decrease your heat loss by radiation. And that's why you wrap it up in aluminum foil. Got that? So that's the reason why you minimize radiative heat losses. It works. Okay. Now, what's next? Now, along with emissivity, right? So if you have a surface that's hot, it emits heat, right? But what happens is, of course, when you go out in the, if you go out at the same temperature, right? If you stand underneath the sun versus you put yourself in the shade, is that why glass blowing? So, oh my God, yeah, Autumn, do you do glass blowing, Autumn? Do you like glass blowing? I can't hear you. Oh, really? Your dad's a glass blower? Oh, I'm such a fan of glass blowing. But yeah, so glass blowing, yeah, it emits a lot of heat. Yeah. But actually, well, I need to go on a bit on the side on that with you, Autumn. Well, how much time do I have? I only have 3-4 minutes here, so why not, right? Let me talk a bit about glass blowing and the heat. Now, the one thing to worry about is when you're doing very high temperatures and radiation, is the distribution of wavelengths. This is the thing you need to be really worried about, Autumn. So if your dad is Planck black body radiation, what you need to be very worried about is not so much the radiation, but rather the wavelength distribution. Because what happens is that as you go up to higher and higher temperatures, so for example, if you look at this thing, as you go up to higher and higher temperatures, notice that the peak, the range of wavelengths go all the way to the UV regime, right? So at very high temperatures, this peak shifts towards shorter and shorter wavelengths. And so you could be emitting some UV light over here, which is very, very harmful, especially to your eyes. And so you wear those goggles, right? And so, for example, I think the hydrogen-oxygen flames can get up to pretty high temperatures like that. Let me see. And also, if you do welding too, that's the other thing. Via the welding, the very high temperatures actually emit UV light, right? Just from the pure black body radiation. And that's very harmful to both your skin and the eyes. Okay. And so that's my aside here. You learn basic welding on my core. Yeah. See, there's a lot of things I like to watch people do, but I don't like to do. Kind of like sports, welding, it's the stuff I see people do. I'm a big fan of YouTube besides just your videos. I do all the other stuff that people do. I like watching welding videos too. It's so relaxing. I'm not kidding you. Okay. Now the next thing is that, of course, besides emitting radiation, surfaces also absorb radiation, right? And so it goes like this. There's this thing called the absorptivity. And so if you have so much radiation, so G here is the radiation that's coming to the surface, watts per square meter coming at you. Alpha, the absorptivity, right, is the absorptivity of the surface. What fraction of the incident radiation gets absorbed? Now, oftentimes, you see something like this. So you can imagine. See, one of the main reasons I don't really go into detail on radiation is because there's this something called view factors, right? And what happens is that you can imagine something like this. So let's say I got my iPhone here, which is, let's say, hot. So it's emitting radiation. So let's say it's a hot surface, it's emitting radiation. And then let's say I have my iPad here, which is a surface. Do you see the problem you got here? If this thing is at an angle relative to this surface, and this is smaller than this surface, my God, do you see what kind of holy hell type of integrations you're going to be making? Because you got the angle and you got like the coverage of this small plane relative to a bigger plane. Do you see like how many dimensional integrations you're going to end up having to do there? That gets extremely, extremely nasty. The truth is, very few engineers actually go off and do those integrations themselves. Those things have been pre-calculated and referred to as view factors, for, let's say, plane and a plane at different angles, right? But they basically become just like formula to use. So I don't really bother to go into that too much. Rather, is it time for tip check? Or can you spare a few minutes here? Are you guys in a rush to go somewhere? Well, we only have 50 people and it's dropping, so I'm going to stop. So today's a relaxing class, no equations. Okay.
Yeah,